So let's go back into our notes and just recap some of the things we've just recently learned about potential. So back in problem 5, you notice that if you combine the equations for delta V, potential difference, and change electric potential energy for the uniform field, the Q's would cancel. And we got this sort of shortcut equation that delta V equals E delta D. The problem with this is that it was a little bit ambiguous as to what the sign on delta V was, right? We got one answer if we separately calculated the change of electric potential energy as opposed to just canceling out the Q, and part of that is because of the absolute value of Q. But then I told you to really figure out what happens, you just sort of label the positions of high and low potential and look to see what happened. In that particular problem, the electron moved from high potential to low potential, so it had to have decreased in potential. Even if that decrease, that negative sign, didn't show up in the math, we know that has to happen. Because any object going from the high to low is going to lose potential. Any object going down the mountain loses elevation, regardless of what it is, right? And so to sort of bypass that, we're going to put both sides of this equation in absolute value. So this way, it just gets us the amount of the potential difference, and then you just label the picture or think it through as to which way the object is actually moving, whether it's gaining potential or losing potential. And we're going to go ahead and box this equation in, as long as we recognize this is only for a uniform field. Because we got this equation by combining the equation for electric potential energy from the uniform field. Again, it's so essential that we know which equations are for point charges, non-uniform fields, and which equations are for oppositely charged parallel plates, or uniform fields. Okay, so now let's consider different objects within the oppositely charged parallel plates and their different tendencies in terms of gaining or losing potential, but now also in terms of potential energy. So let's say we have, for example, a positive charge, right? So if we take the positive charge, that's like our cooler of food in our analogy, and if we let it go, which way would it go? Of course, the cooler food would roll down the mountain, so the positive charge goes down to the negative plate. Okay, so now in that process, is it gaining or losing potential? Right? Well, hopefully you realize it's losing potential, right? It went from a position sort of in the middle to a position of lower potential. It's certainly losing potential. Now, in that process, is it gaining or losing potential energy? Pause the video and really think it through. All right, so hopefully you came to the conclusion that it is losing electric potential energy. And we just go back to our idea of gravity, right? If you were to move an object in the same way, you would be taking maybe like your calculator in your hand and moving it down, right? And so obviously the plates don't have to be vertically aligned, but I did it this way so we can really connect it to the idea of the mountain. But no matter how the plates are aligned, any object that starts in the middle, any positive object that starts in the middle and then goes towards the negative plate, well, it's going where it wants to go, right? That's a loss of potential energy. Just like if you let an object go and it rolls down the mountain or it falls, it's going to a lower height, it's going closer to where it wants to go, it's losing gravitational potential energy. So this positive charge, left to its own devices, tends to lose electric potential energy, going where it wants to go. Now what happens if we change it to a negative charge? So if I take the negative charge and let it go, where does it tend to go? Sure, towards the positive plate, of course, it's attracted that way. There's the helium balloon rising up in the air. And so in that process, is it gaining or losing potential? Hopefully you said it's gaining potential, because look, it's going up the mountain. If it starts in the middle and it goes towards the positive plate, well, the positive plate is a position of higher potential, so it's going up the mountain, it's gaining potential. Now what about in terms of potential energy? Is it gaining or losing potential energy? Really pause the video and think it through. Hopefully you came to the conclusion that it's losing electric potential energy. Potential energy, right? Be very careful. Potential energy is large in a system where it doesn't want to be, small in a system where it does want to be. And this negative charge is right where it wants to be against the positive plate. That's a position of lower potential energy. And so we see the general case here is that all objects tend to lose electric potential energy. And be very careful the distinction between potential and potential energy. The potential has to do with the actual position between the plates, and the plates themselves determine that potential. And this, again, goes right back to this idea of delta V equals E delta D. A great reason we use this equation is that it totally eliminates the charge. This is like when we canceled the hiking trip, right? The potential is just there because whatever creates the potential, the mountain in our analogy, the plates in this case, and no matter what, the positive plate is the high potential and the negative plate is the low potential. So any object that goes towards the negative plate is losing potential. Any object that goes towards the positive plate is gaining potential. In terms of potential energy, now you have to think about where the charges want it to be. Now, of course, we can relate all this, if you want to look at this from a mathematical perspective, with our original equation relating change in potential to change in electric potential energy. Let's consider the positive charge first. So the positive charge, left to its own devices, loses potential, which means it goes down the mountain, which means delta V is a negative number. Q, for our positive charge, is a positive, right? And so if this is negative and Q is positive, that means that delta PE must be negative as well. That's how the math works. So the positive charge that loses potential is also losing potential energy. Now consider the negative charge. The negative charge, left to its own devices, goes up the mountain towards the position of higher potential, so it's gaining potential. That means that delta V is a positive amount. The charge itself is negative, however, right? And so if this is a positive amount and the charge is negative, what do you know about the change in potential energy? It must be negative as well, so the negatives cancel for a gain in potential. So I find that most students really understand one or the other, really the change in potential or the change in potential energy. So really focus on the one you're more comfortable with, and then you can use the connecting equation here to get to the other one.